Okay. So we want to try to understand what the word isotope means. Now, one of the most important things I think people need to understand about atoms is, and the periodic table, elements, and so on, is that the number of protons determines the name of the atom. So as soon as I give this empty space a proton, the name of that atom or ion is hydrogen. If I gave it 2, it would be helium. And it doesn't matter what I do to the neutrons or the electrons, the name remains the same. The name is entirely dependent on the number of protons. Okay. So now, if we go back to hydrogen, for example, the standard hydrogen that we see in the periodic table will have a mass number of 1. Once it's a neutral atom, it will have one electron to cancel out the charge of the proton, and that's hydrogen. Now, there are other types of hydrogen that exist. Some hydrogen atoms actually have a neutron as well. This would have a mass number of 2, and some hydrogen atoms have 2 neutrons, but the vast majority only have one. Only have a proton and 0 neutrons. They would have a mass number of 1. But these other hydrogens do exist, but they're quite rare. Now, these different types of hydrogen we can call isotopes of hydrogen. And in fact, the thing about some isotopes, we can say that they are unstable. Now, unstable isotopes are isotopes or atoms that don't hang around just as they are. They don't stay hydrogen for very long. In fact, these isotopes of hydrogen have got a special name. The one that has a mass number of 3, in other words, has 2 neutrons, is called tritium, and the one that had a mass number of 2 that you saw a moment ago is called, I'm going to spell this wrong actually. Let's have a look. Deuterium. I think it's deuterium. I'm going to just I think it might be. I might be doubting myself, but let's just check just in case. Oh, I actually got that right. So tritium, deuterium, and just regular. I don't know what the regular one would be called. They're all hydrogen, but they actually have these special names. So if I make water H2O using either tritium or deuterium, the water molecules are actually going to be heavier than normal water. It'd have a larger density, a higher density, if I took a liter of heavy water compared with a liter of regular water, because each atom of hydrogen is going to be heavier than the atoms of hydrogen that are normally in water. So that's what you may have heard of heavy water. That's what heavy water is. Okay. Now, okay, so that's basically what isotopes are. If we look at this, sorry, go on. Hang on a second. Yeah, okay. So let's look at these isotopes of hydrogen in this simulation. Here's the symbol of hydrogen here. This is its abundance. So if I were to take a load of billions and billions of hydrogen atoms, then that percentage would be the one that we are more familiar with. But this one does exist, but there's only that much of it. And this one exists too, but there's only what we say a trace amount, and as you can see, it's unstable too. Let's just see a little bit more about what unstable means. Here's tritium here. If I press play, it wobbles around and turns into helium. Let's have a look at that again. I don't know if this wobbling is very scientifically accurate, but nonetheless, it sort of represents it being unstable. If we look at it carefully, what's actually going on is one of the neutrons is turning into a proton. And when it does that, it actually gives off these 2 other particles. And I'll pause it this time if I'm quick enough. We'll be able to see what these other 2 particles are if we're careful, if I'm quick. This one's going to take ages now, isn't it? Oh, there we go. So it's become helium. blue particle and a green particle. If we look up on the legend up to the top right, we say that's the neutron, that's the proton, and the blue thing is an electron, and the little green one is called an antineutrino. Now, the most important thing to realize here is that there was no